And that is the one we try to use treatment with antibody for the for this two cytokine, but we didn't really get to conclusion of that. And so far, it's lived this way. But it convinced us that this HIV rats does have the immunodeficiency that. Regardless of the elevation of cytokine, it just didn't show that LEA increase that we call that the initial stage of the response initial step of the immune response cascade. And then the next characterization of this animal is the learning and memory behavior. We know that HIV patient has a cognitive deficit, and so we try to characterize how this animal, in terms of their learning and memory behavior. Classically, would use the so-called standard Morris water maze that would respond to the visual clue, the animal. However, I forget to mention that the animal, HIV transgender, has a phenotypic is a cascade, the catchers. So they didn't really see the visibility as compromised. So the characters that would present a challenge. So therefore, we developed this modified non-visual water maze in the very earlier time that use audio, use olfactory, and use textural to characterize how this animal's behavior responds to the water mazes, their performance in the water maze. So the auditory said that we have a song indicate here, and then also the flavor of the fragrance of the mint versus vanilla, and then also the fish net at this quarter. And the prey form of this, the animal can get out the water is located in this direction, okay? So the data shows here is the HIV rats would take a much longer time to find the prey form in the water, in the pool. And then when the difficulty of the performance in the swimming increase, for example, changing the direction when we put into the pool, and then also reverse the direction, then the HIV rats would take a longer time. The performance getting more poor. The difference would be more difference in compared with control animal. The most likely is when we start monitoring how they swim. Okay, the control animal will swim along the side of the pool, get to the location of prey form. But for the HIV rats, pretty much is kind of running around like a chicken without head. And for the transgenic animal, pretty much close to the control animal. So after we have done this study, we began using only the HIV rats and then the F344, because transgenic rats, they charge us same price as HIV rats. So we most of the study, after this study, that we had actually has only one control, which is F344 control. And in the earlier time, kind of accidentally, we do this locomotor activity because just in the earlier time, we say we report that doesn't have deficit of locomotor activity when we put into the box to see that. But for this locomotor activity, we call the wheel running test. It was very surprised to us that HIV rats seems running on the pool, kind of getting higher, and then they are running much more than the F344 rats. The running wheel, or wheel running for rodent, is considered as a motivated behavior. And if you ever play with a guinea pig, in the daily life, we probably don't use rat and mouse, but their behavior is similar. You put that on the wheel, they will run in, they are happy. And then it seems that they should be running to the certain way, elevate and then patrol. For the control animal, we patrol to that. But for the HIV rats, they seem to running more and more and more. Okay, when we look into because this is a motivated behavior, when we look into the literature in terms of addictive substance usage of substance, they actually have some very interesting information regarding how the wheel running correlated to the cocaine use in the animal model. So actually, this is really the study, the behaviors in the earlier time that we start thinking about that the HIV and the substance abuse could possible this persistent presence of HIV viral protein will contribute to some kind of change in the brain biochemistry, and then will lead to this behavior, addictive or some kind of addictive prompt behavior, i.e. wheel running or use of addictive substances. That's our very wild hypothesis that time. And we did go on with individual substance addictive drug study, but at the same time, we also thinking about why don't we use RNA sequence, do the analysis to compare the brain region between these two animals, see what's so-called brain biochemistry changes. Okay, and so this is RNA sequence study analysis that we compare the read from the between the two strands animal, raw read, map read. All this read is in units of million. Okay, and we have a whole bunch of reading here. I always just look very cross that when the data come in. I say, okay, we got it. And then now they also give me this one, the mapping, percentage of mapping. So I look at that, I say, okay, they are very similar. What's the difference? I don't really quite see the difference. And then that reminds me of that when you walk in the forest, each forest, it looks similar. So, but then when we start looking into taking the computer sciences technique, start looking into comparing the three different regions, comparing how this read, the overlapping. So we start constructing all this mapping, 16,637, the overlapping there, 16,676, the overlapping of the genes. Then, okay, so that means they have subtle difference. Subtle difference in the MRI, they may see the structure differences. In here, we show some difference. We look into the literature, then we start teaching out all these changes of the gene, and then group into the biochemical pathway. It grouped into three pathways, three class. One is immune response in yellow, and neurotransmission changes in blue, and then white is a neuronal survivor gene being changes. And I think I would say that by looking at this, I say, wow, of course, immune response being changed. Well, why not expect that? Of course, expect that. But when the brain region has all these immune response changes, what do we expect? So we start doing all this connectivity mapping things, and then we see that in the prefrontal cortex, in all this connection, immune response had all the changes, neuronal survivor overlapping there. And then move on to the next one, the hippocampus. Similar things are seen that, but immune response is still most dominant, this one. And then we go on with the striatum. Then we're seeing that, again, the immune response is still the biggest cluster, all the changes. I'm sorry, this one is dancing around for me. Okay, and so we actually when we come to realize that the immune response related to the pathway is one of the pathway altered in the HIV transgender rates. We draw this conclusion in our paper. Then we also are making all this mapping based on all this pathway. I don't know how to do this one. Oh, it's not moving. Okay. So we put all this gene in here, neurotransmission, and then neuronal survivor, and then also immune response. We come to all this that linked to the deficit in learning and memory, and then also the neurodegeneration. And also in this part, we believe that neurotransmission changes will lead to the drug addiction, depression, and other psychiatric disorder. We did not really, at that point, to point out that immune response has direct effect to the drug addiction. Maybe not. Okay, and then in our later on, go back to our animal model study, it actually directed to is routing, changing the brain biochemistry, and they lead to the addiction. Okay, in the next several point I want to make is showing that we study in the 3 different drugs. I really don't know how to put this in. Okay, the first drug that we study is the methamphetamine. Okay, methamphetamine has been known that would induce behavior sensitization. That means then that day one you treated methamphetamine, it would have induce the stereotypical behavior study, particularly head bumping, head movement. And then next day you give same doses, the response will be enhanced. And then day 3, day 4, day 5, day 6. And then when we compare with HIV transgenic rats versus the F344 rats, the behavior sensitization induced by methamphetamine is much more striking compared with F344 rats. And then at that time, then we measure the dopamine receptor. It shows that dopamine receptor expression changes. Later, we decided to look into in the area called nucleus accumbens, let's see how those expression of the cytokine as well as the receptor being changes. And then it's very interesting to see that the methamphetamine actually changed the cytokine expression in the brain in that particular area, nucleus accumbens. And the HIV transgender, given the methamphetamine, the change is further enhanced and either increase or decrease. And currently, we are trying to use CB2 agonists to activate the cannabinoid type 2 receptor, see if we can reverse the methamphetamine induce of the behavior sensitization, particularly in the HIV rat. The preliminary data actually come out pretty positive. That seems that the activation of the CB2 receptor can reverse the methamphetamine-induced the cytokine expression in the brain. And the next one is I want to show you some morphine study. This one is probably the most extensive study we have, particularly because the HIV and morphine usage in the past 20 years that people keep on saying that whether the HIV morphine usage, opiate usage, would enhance the HIV expression, the progression of HIV into AIDS or not. And then they back and forth for the argument by when they using the monkey model. And I think the difficulty for the monkey model is because they cannot have a large number of the animal because it's expensive of the monkey. And so in this case here, that we compare with the HIV transgenic rats and F344 in terms of how the mu-opioid receptor expressed in this animal. And it shows very clearly that mu-opioid receptor expression is increased in the HIV transgenic rats in both, I would say that, in the tissue we examine, including macrophage as well as in the brain. And then we mapping this mu-opioid receptor expression, and we strikingly found out that the mu-opioid receptor that is actually located in the glial cell and the astrocyte. And then the increase of the mu-opioid receptor actually is because increase of the microglia and then also the astrocyte. And then I was asked when I present this data, I said, well, but mu-opioid receptor suppose that in the neuronal cell, and then that would lead to the behavior changes. And then so during this time that we actually did a cell culture study, we didn't do it's not that easy to do the animal models that when we have this showing that the glial cell, for the detection of the mu-opioid receptor in the neuronal cell is just not detectable at that time. Okay, and so we actually use the cell culture that challenge with the macrophage given the LPS, and then take the condition media, lay over on the neuronal cell, and then increase those mu-opioid receptor in the neuronal cell. So for that, we kind of skip for the behavior study and then taking advantage of cell culture. and then go on with jump into the behavior study. Here is the tail flick latency test. Tail flick detection, how the response to the morphine, see if an animal was lay on the hitting on the heat and then give the morphine, and then measure how long the animal flip the tail. So that's longer longer time to flip the tail upon the morphine treatment. That suggests that the morphine has the painkiller effect. And in this study, that is clearly show that in the same dosage of morphine, we use this cumulative dosage of morphine, same dose of morphine, that the tail flick latency is much longer in the HIV rats. That means that you give a same dose of morphine, that for the F344 animal, the tail flick would be much shorter, would show the latency would much shorter. That means morphine effect is much more stronger on the HIV rats. So in other words, that when you come down to this is when we use this for painkiller, yeah, the HIV morphine probably has more effect. But when you come down to the taking morphine as a pressure or become the addictive substance, let's see how the difference there. We use the so-called condition place preference, CPP, to measure HIV rats. And then this time we also decided to have a TG control animal, and then F344 rats. When we give the animal in the morphine and tie the morphine treatment with a certain box, it's called condition, CPP. And then when we build that animal has develop their CPP behavior or reach to this stage, that after certain time that we call it precondition testing, 3 days or 14 days morphine condition. After that, we have post-condition test. So then after this one is when we show that all these animals develop the CPP with morphine. Then we start taking the extinction testing. That means we stop giving the morphine, see how the animal would dissociate that box with the morphine, and it will not go to that box again. So that very interesting. Then we see that the HIV rats take much longer time to dissociate their tighten with with their dissociate extension, the test, dissociate their condition preference. And then after that, we try to reinstate the animal back to see if they would give the further treatment with morphine. They would go back to the condition CPP stages. Very striking to us, HIV rats doesn't really easy to be reinstated. And then at that time, we're just positive why, because it seems it's tied to stay with the CPP. That means they remain with the morphine with the environment much stronger than the other control. But when we want to reinstate, it didn't go back. And later on, when we start putting in that, this animal actually have learning memories issue as an earlier time stage. That makes sense. Okay. So then the other drug I want to talk to you that is the alcohol use. And this is my current research heavily emphasized on the alcohol for the very reason that I'm interested in alcohol, because alcohol has very different challenge to scientists. Okay, morphine has a mu opioid receptor. You go to see the receptor. Alcohol doesn't really have a specific receptor. Alcohol also can infuse into the cell easily. Actually, alcohol beans suggest that they have certain kind of so-called protein target, but not really characterized as the other receptor-mediated drug action. Okay, so now when you go on a drink, when you say one drink, okay, one drink by definition by NIAAA is equal to 12 ounces beer, or 5 ounces of wine, or 1 glass shot of liquor. And because it depends on the different concentration, liquor is 40% alcohol by volume. Beer is 5 to 8%, and then wine is around 12 to 15%. So the question here is, if alcohol concentration make a difference, when you have shot glasses versus a bottle of beer, will that make any difference in your body, or does that make any difference in terms of developing of addictive behavior to alcohol? So literature showing that when you have different concentration of exposure to different concentration of ethanol, that the body actually digests the alcohol in a different way. In here shows that the blood concentration, blood ethanol concentration is different, brain concentration also different. So that gives us a hint that the concentration difference should be measured. And in the earlier time, much earlier, in the early 90s, that we studied a protein called proto-oncogene, fast proto-oncogene protein, and to see where is the site of action in the brain of certain stimulus. Here is alcohol. And then it will show that little dot of the fast proto-oncogene protein, which is a nuclear protein, so it's round dot. And based on that fast immunocytochemical staining, we actually report exactly 20 years ago that 7 nuclei, brain nuclei, would respond to the alcohol treatment. But one of those is called superoptic nuclei, only responds to alcohol treatment if the same dose of alcohol was given the concentration of ethanol concentration much more than 32%. That means compared with the beer, wine, and liquor, that means that when you drink a liquor, only you drink a liquor that this superoptic nuclei would be activated. Okay, so with that in mind, that we studied the alcohol consumption in the HIV transgenic rat. Did I run out of time? Okay, I'll run it. How about we run it quick here? Okay, so the study that is we compare with the 3 different concentration of the ethanol to the rats. And then we measure their locomotor activity. We found out that the animal we given the 3 group, the 2 different concentrations given same dose. When we give a higher concentration of the ethanol, the locomotor activity would remain in the HIV rats, only HIV rats, much longer than the F344 rats. And with that, we measure the blood ethanol concentration. We strikingly found out that HIV rats' blood ethanol concentration remain much higher, remain elevated much longer than the F344 rats, particularly in the higher concentration. And then we go back to the literature, found out that their report that by Yuri Persitsky that they found out that the HIV patient, their alcohol metabolized enzyme actually being it's not activated. That means they have deficit of the ethanol metabolized enzyme. And then when we check on this animal, that in response to the alcohol treatment, F344 rats, the enzyme elevated, that means increased activity. However, HIV transgenic rats, they do not have that elevation of the activity of this enzyme. So for this, we go back to say that, well, what does this animal study do anything good for that? We go back to the literature or search out with a whole bunch of literature that's showing that the general population, compared with general population, HIV-infected individual actually much heavily use addictive substance. That actually, our animal model study actually linked together with this literature that suggests maybe the HIV patient under the CART, just like this HIV transgenic rats that has gay and POP being removed, but the other several viral proteins still activated. That may be the reason why that this animal, through the changing the receptor, changing the metabolized enzyme, in the case of alcohol, in the case of the morphine use, the receptor being changed. And then that lead to they have use of the addictive substance much higher than the general population. I apologize for the time. Yeah.
Next is Dr. Sulie Chang. She is the director of the Institute of Neuroimmunopharmacology and a professor of biology science and neuroscience at the Seton Hall University in New Jersey. So Dr. Chang has been, she certainly is very, very founded scientist, and she has published over 1,000 papers in the field. So Dr. Chang has served on several editorial boards, including the Journal of Neurobiology and the Journal of Neuroimmunopharmacology. So now let's listen to Dr. Chang's talk.
Just click here. What's going on?
Oh, here.
Don't have.
No, that's doing it. Screen.
It was okay earlier. Here.
Oh, here we go. No.
Still. No, go to
Sure.
click this one.
Yeah, but it's not.
Okay,
There we
and
go.
then here.
Mm-mm.
No. It's still not up there. Okay. That's okay.
But it's not. Okay, there we go. Yeah, that's fine.
Maybe this one.
You're gonna have to hit it here, okay? Because it's not.
But how do I?
Sorry, it's not my computer, so I'm just helping out here in this room.
But it won't move.
Yep. There we go.
All right.
Tap it. Okay.
Okay, it's challenging. Good morning. Thank you for inviting me here. But first, I need to correct my publication is over 100, not 1,000. I wish, and I don't think I will see people over 1,000 publication. Yeah, it's very happy to be here, and as everybody say about this. This kind of meeting has all the expertise here, and as I say, it's very effective to learn things from various expertise. And today, actually, I would like to share with you almost like 10 years thinking or working with an animal model. The first, I was putting that out as a model for the NeuroHIV, and now I'm come to the point, try to tell you that this model can demonstrate how infection, systemic infection, lead to the addictive usage of the addictive substances. Okay, let me see if I can move on. Okay, what is HIV? Just Lynn mentioned that maybe this audience need a little background, and actually it's kind of refreshed my memory. So HIV, what is a disease that considered as immune system dysfunction. However, just like one of the neurobiologists mentioned that HIV actually is a genetic the mechanism of this disease causes by the genetic. That means that HIV virus enter into the genome and then control, maybe so carry the genome and deliver, produce the more virus in the body after it's infected, and then cause the immune system dysfunction. And I like to point out the figure, bottom line there is once the HIV infection, very quick. I would say that within a week or two, as I understand that the HIV virus actually will enter into the brain compartment. That means that the virus actually enter into the brain, and then that cause very dramatic the neurobiology issue, the brain dementia. And well, about 20, in the past 2-3 decades, HIV virus and then the substance abuse, it seems that has been, for example, the substance abuse, the drug abuse has been identified as a comorbidity of the HIV infection. And then NIDA's director in the past 10 years, Dr. Neuroimmunology has been very successful to convince the general population, particularly HIV, NIH. So, and NIDA has tremendous funding for the HIV research. And in the earlier time that many studies show that use and abuse of addictive substances, morphine, cocaine, methamphetamine, alcohol, actually been shown to accelerate the progression of HIV and then also the HIV-associated neurocognitive disorder, HAND. However, the nervous system, immune system, actually we know from yesterday that we have a bidirectional link between these two systems, actually has major implication that the treatment of HIV patient actually has a greater risk for substance abuse. And today this is what I would like to share with you, our animal model study that seems to direct me to think in this way. That's why I'm saying that because in the past 20 years, this is a combination antiretrovirus treatment. It's quite effective. The patient infected with HIV will not face the dying death promptly after the infection, and then they dramatically increase the death rate for the HIV patient, and then however, it didn't really decrease effect of HIV on the CNS. That's why we call it HAND. So I believe that perhaps probably 10, 15 years by now that development of animal model for neuro-HIV research has been quite essential. And then several animal model that been developed for the HIV infection study that, of course, including that SIV, the monkey model, which is non-human primate, and then also the cat, also using the SCID mouse, the humanized mouse. And then today I will talk to you about this HIV transgenic rodent model. It was originally developed. I didn't develop this mouse rodent model. The mouse model was first developed, but somehow this mouse didn't really develop the AIDS symptom. So the scientists read it all in the University of Maryland. They move on to develop this transgenic rat. Then the transgenic rat in the many study in the past 10, 12 years, maybe 15, by now it's maybe 15 years, it shows that it's an alteration of central motor gating and behavior, and also that in our own study, we also show that the vitamin A, in our study, this is Walter Roy's study that showing that vitamin A deficiency is HIV-associated neuroinflammation and the mu opioid receptor, including the study from ourselves. I'm going to show it to you. And just a few words about this animal model. Well, HIV has 9 viral proteins. 2 of them called gay and Paul that are responsible for the viral assembly to make the viral protein produce the virus, and then also responsible for the reverse transcriptase. That means that control the replication. So for this HIV transgenic rodent model, the scientists actually remove the gay and Paul. So therefore, the transgenic rodent, they will not have a viral replication. However, they have the other 7 viral protein continue expressed in the rat. And so by thinking carefully that HIV upon the infection very quickly get into the brain system. However, upon the combinational antiretrovirus treatment, or earlier time called HART, that the patient, they had limited or controlled the replication. However, the virus in a low level, as Lynn just mentioned, that it still continue in the brain. And compared with this animal model, that GAN-PO was removed, but the other viral protein is continuing expressed. So early, about a little bit more than 10 years ago, I began proposing that this animal model, it mimic HIV-infected patient on CART. So this model is not HIV infection model. It doesn't have infection, but it's mimic HIV-infected patient on CART. When I began using this model, I was not never being considered myself as a behavior neuroscientist. But then NIDA, my program director, said that, well, you must characterize this animal model by various aspects, including behavior. So we went on. Even by today, we still continue to characterize this animal. And then by in the earlier time, we get on talk about their growth, their behavior, and their immune responses, and then also locomotor activity. I'm going to tell you one by one, and then including the RNA deep sequence. So the HIV transgenic rats, its growth continues. It's just smaller. The size is smaller. And it will continue growth, and it's without, but no sign of illness in the early stage. And then no obvious locomotor deficit either, okay? By the time they reach 18 months, then it starts showing the earlier decline, the wasting, and then leading to the earlier death. And then pay attention on this 18 months, because in the next slide, I will share with you that we actually, when we began try to use this model to study the aging, because by this year, 50% of the HIV patient being diagnosed actually is over 50 years old. So aging is the issue, not only to us, it's also the HIV patient. So we begin comparing the older age. I believe is we use the 2-3 months, and then middle age, the 5-6 months, and then over 12 months, 15 months. And it's showing that the immune response changes, and the immune cell population also changes. I want to call your attention that neutrophil, when they up to the 18 months, and then the neutrophils' elevation is much higher than the other the control animals. And so since the immune phenotypic difference, of course, that this animal, we need to characterize how it responds to lipopolysaccharide, which is a model compound that we use to induce inflammation. Just Lynn was mentioned that. And at that time, we have use two different control. One is a strength control called F344, and then also the transgenic control, and then HIV rats. And then when we challenge with LPS, at that time we measure only two, just generally divided into the pro-inflammatory cytokine, TNF-alpha, and the anti-inflammatory cytokine, interleukin-10. And see the two control animals that in response to the LPS treatment, then the elevation of the anti-inflammatory cytokine and the pro-inflammatory cytokine, about 2, 3, 4 increase than the control without treatment. For the HIV rats, very striking to us is anti-inflammatory cytokines. The elevation is much higher than the, pro-inflammatory cytokines. Elevation is much higher than the anti-inflammatory cytokine. So we will say, well, expect it to be so, and then we say, well, the elevation of cytokine got to do something about the immune response. And at that time, we using a technique called intravital microscope can measure how the leukocyte adhere to the endothelium. In here, this is the endothelial cell that is called LEA, and this is we consider is initial step of the inflammatory response cascade. And for this, when we have, and it's also literature work saying that the pro-inflammatory cycle such interleukin-1 beta, TNF alpha would enhance LPS response. So we measure the LEA using intravitreal microscope of the 3 group animals. And that's, again, control, TG control, and then HIV transgenic rats. And then for this particular technique, we also need to have the chemoattractant, which is to make sure the tissue, the LEA response decrease, increase is due to the cytokine, not due to the tissue damage. So that this one, that the chemoattractant to demonstrate that all the tissue are okay, and for this bar, but for the control animal, that the treatment with LPS, we see the increase of LEA. This one, LEA. Corresponding to the elevation of the pro-inflammatory cytokine. But for the HIV rats, that LEA increase just was not